All right. Good morning or afternoon or whatever time it is that you're watching this. So this is the second half of section 6.1, Exponential Functions. And we're going to start here at applying the compound interest formula. And so basically, one of the first examples we'll discuss is in an interest earning savings account. And when that happens, you're continuously reinvesting, meaning, you're paid some interest according to a percentage, and then you just dump that back into that account. And so it continues to what we say compound. And so some terms that are important here are going to be the APR, which is the annual percentage rate. And we also call that the nominal rate, is the yearly interest rate earned on an investment account. And so we use that term nominal when the compounding occurs more than once in a year, because when that happens, the actual effective interest rate ends up being a little bit greater than the nominal rate. So this is something that's really, really powerful and pretty important to kind of have your head wrapped around. And so just looking at this table, it just provides a little information on the value after a single year if you had $1,100 invested in one of these interest earning accounts. So if it compounds every year, you'd have $1,100 after a year. Semi-annually or twice a year, you'd have a little bit more because you're receiving more compounding. After that, you'll have a little bit more if you're compounding quarterly 4 times a year, and then a little more for monthly, and even a little more for daily. So again, the more compounds we have, the actual effective rate actually goes up a little bit. So this is the compound interest formula. And so just picking it apart, A of T is the account value as a function of time. T is always measured in years. P is the starting amount or the principal. R is the APR expressed as a decimal or the annual percentage rate. And N is the number of compounding periods in a single year. So the first example says that if we invest $3,000 in an investment account, paying 3% interest compounded quarterly, how much will the account be worth in 10 years? And so, one of the first things I like to do is I like to kind of get a handle on what all of the information I'm being given is. And so the time is 10 years. The rate as a decimal is 0.03 or 3%. N equals 4 because when we're compounding quarterly, that means 4 times a year. And then finally, P, the principal, is $3,000 for the $3,000. And so utilizing the compound interest formula, that's P times 1 plus R over N to the N times T power. We can just plug all those things in to get the value of the account after 10 years. And so 3,000, 1 plus 0.03 divided by 4 times 4 times 10. Or excuse me, to the 4 times 10 power. So if you plug all that into your calculator, remember in the first part of this section, we talked about making sure that we are using the correct order of operations when we are calculating these sorts of exponential functions. And so you would end up with $4,045.05 in 10 years. So basically in interest, you had earned about $1,045. So for this one, if you want to give it a try and see how you do, I encourage you to do that. Pause the video and then come back to check your answer. All right, so here is what you should have gotten. It'd be $3,644,675.88. Moving on to example 9, this uses the same compound interest formula that we used previously. However, now we're wanting to solve for P, the principal. And that's fine. We're just going to kind of attack this the same way we did. Let's pick apart everything that is given to us in the scenario. Like this time, it's going to give us the amount in the account, which will be $40,000. T is 18 because they want to know, how how much they need to invest to get that value over 18 years. The rate is expected to be 6%, and the number of compounds is semi-annually, so that's 2. So let's go plug all these values in. This will be 40,000 for the account value. We don't know P. 1 plus 0.06 divided by 2 to the n times t. So that's 2 times 18. Again, for the order of operations, we need to remember all of this kind of needs to be handled first. And then we'll be able to simply solve for P using the normal algebraic methods. So 40,000 equals, if you evaluate this number, you'll find that this is approximately 2.8983. And from here, it's just a matter of dividing both sides by this 2.89, solving for the principal. So you would obtain that they need to make an initial investment of approximately $13,801 in order to have that grow to $40,000 over the next 18 years. So that is utilizing the interest formula to solve for the principal needed to achieve a certain value over time. The next thing is, for a second, we're just going to kind of talk conceptually about what the base E is and what the number E is. And so we learned earlier that the amount of interest earned increases as the compounding frequency increases. So looking at this table is the value of a single dollar invested at 100% interest for a single year, compounded at various frequencies. So you'll notice that it's growing. You know, if we're compounding once, we're compounding twice, we're compounding 4 times, 12 times, 365 times, whatever that is. 8,760 times. Once a minute would be 525,600 times. And once every second would be, 31. Looks like that's 31 million and some change. So notice it's increasing relative to the initial amount a good bit as we're moving up. But as we really, really start compounding really frequently, especially kind of in these values, you see that we're kind of slowing down in how much that increase in the compounding helps us out. And it kind of caps off at a particular number. And that number that it caps off at is actually the number E, which is a number very similar to pi in that it has a specific value, but we use it so much that we've assigned it its own special symbol, just like we did pi. It is irrational, just like pi, in that its decimal expansion does go on forever with no repeats. And this is some information about the number E. So the number E can be expressed as the limit of this expression as n increases without bounds. So as n gets extremely large, this expression approaches the value of E. And so we use that an awful lot in many applications. And fun fact, if you guys know who to be mad at, just like it was Bombelli with the imaginary numbers, now you can be angry at the probably one of the most respected and prolific mathematicians of all time, Leonard Euler. And so that's why we named it E for him. So in any case, let's learn how to use E. So let's first use a calculator to find different powers of E. And so there's going to be a button on your calculator. I don't have my software available right now to show you exactly where that is, but it's going to be above one of the other calculator functions. And so above one of the functions on your calculator, so this is a button, you'll see in kind of green in those second functions, you'll see the e to the x above that. So you'll hit the second and then that button, and it'll allow you to place e to a certain power. And so make sure you can find that button. And if you can't, please see me on first thing on Monday so I can show it to you. And we would find, plugging that in, that e to the 3.14 is 23.10387 approximately. And so now give it a try. Find that button on your calculator and round the value of e to the negative 0.5 power to the nearest 5 decimal places. You should end up with 0.60653 approximately. So the reason that E is important is that is the base of this function when the compounding or the growth is continuous. It's instantaneous. And so every possible instant we are recompounding. So most real world phenomena do use the number E as their base. And that's going to be used in finance, computer science, most of the sciences, physics, toxicology, and fluid dynamics. So lots of applications for this very, very special number and idea. So we have a very similar kind of idea to a normal exponential function. You'll notice here that you kind of can notice a parallel between the function f of x equals a b to the x that we studied in the first part, except for now b is the specific e, and the x is r times t, which is kind of the rate times the time. And so again, here you can refer back to that if you need to know what each of those values mean. And this is actually really important. If the r is greater than 0, then this is growth. And conversely, if r is less than 0, then it is continuous decay. Now, in specific business applications, we change that A to a P for the principal, which you should remember from just a minute ago. And then the parameters are similar. Here's your how-to box. If you need to go back, it's a very clear step-by-step set of instructions to solve problems of this type. So example number 11 actually asks us to calculate how much is in an account if someone invests $1,000, earning a nominal 10% per year. That's your APR, but it is compounded continuously. And so instead of using the normal compound interest formula, we want to use the continuous compounding formula. And so that's going to be the A of t equals P times E to the RT, PERT. So let's pick apart what we're given. So the principal is 1,000. The nominal rate, or the APR as a decimal, is 0.10. The time elapsed would be 1 year. And so just plugging all that into our formula here, we'll be able to easily solve for the amount in the account. So this would be 0.10 times 1. And just plugging all that in your calculator, you'll obtain that the amount in the account is $1,105. Whoops. Let's fix that. $1,105.17. So if you want to give one a try, I encourage you to do that. Pause the video, come back and see how you did. All right, so you should have obtained that approximately the value of this investment after 30 years would be $3,659,823.44. So the fact that this number is so big really should encourage you to really invest in your 401k or your retirement account as early as possible. I'm talking like your first job, right? Because even putting a very small amount into that account early is key. Because what happens is there's a certain point that growth, while it's very slow at the beginning, there's a certain point where it just goes crazy. And if you start early enough, then you'll be looking at numbers like this when you're ready to retire. And so, but if you miss that window, then you miss the power of the compound interest. And so just a side note of why that's so important. If nobody's told you that yet, I'm telling you now. Now let's talk about continuous decay. And one of the applications is decay of radioactive isotopes, such as radon-222. And so for this, whoops, my bad. So for this, we'll not use the financial applications version of the continuous growth and decay formula, but we'll use the regular application where the initial value is A. And so let's pick apart what we have. The rate here would be 0.173. And the time elapsed is actually going to be 3. And the initial amount, A, would be 100 milligrams. So there's one important thing that you need to consider when you're working with a decay problem. Remember earlier we said that the rate is going to be negative if it's decay. So because it specifically says decay, we have to go back and account for that by adding a negative to the rate. And so don't forget that, because if you don't, you're calculating the growth, which is not what's happening here. So the ending amount of radon 222 would be, let's see, this is 100 for A times E to the 3 times negative 0.173 power. And plugging that into your calculator, you would obtain that there would be approximately 59.5115 milligrams after 3 days. And so now it's important that you try number 12 because I'm going to show you something about the calculator output. So go ahead and do that and then come back and we'll talk a little bit more about scientific notation. All right, so you should have obtained something in the calculator that looks some kind of like this. So this is the calculator notation for scientific notation of this number, which means this negative means that we would move this decimal place to the left 26 times. And so that number is super, 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 super close to zero. Very close to zero. So of course with the exponential, because there is that horizontal asymptote at zero, we never actually get there. But for this application, for all practical purposes, it is practically, not exactly, but practically a value of zero. And so that's important to understand. Y'all should understand what this number means and what this calculator input means. And so, that being said, that is all for 6.1. Be prepared to work some problems in class on Monday. So I hope this was